Hello all of you. In the last lecture we have been discussing the grand canonical ensemble, and before that we have discussed the canonical and microcanonical ensemble. In this class we will discuss the very last ensemble, that is called the isothermal isobaric ensemble, for which the Gibbs energy is a thermodynamic function. This is one of the most commonly used ensembles for the purpose of molecular simulations, and also it is more relevant to the experiments, because in experiments we typically keep temperature and pressure as control variables. So, the process in which we will build the equations for the ensemble will be the same as we have been doing, except that we will have a new definition of the partition function corresponding to the isothermal isobaric ensemble, and the average properties will again be written in terms of partition functions, but for this new partition function that we determine for the isothermal isobaric ensemble. So, the basic idea for the isothermal isobaric or the NPT ensemble is the following. So, pressure is a control variable. That means, if I look at systems in the ensemble, the conjugate variable volume will not be constant. The volume can vary in the systems, but the pressure will be constant. So, in this case, unlike say the canonical ensemble, when the NVT was the control variable and therefore volume was a control variable. In this case, what we will have is NPT will be the control variable. We are controlling the number, the pressure and the temperature. But again we will have a large number of systems in the ensemble, let us call it A systems, but now they are going to have different volumes. Every system will have a different volume, unlike the previous case. So, therefore, we can now define the occupation number as something like AVJ, that corresponds to the number of systems with volume V, the volume can vary, and energy, and we are referring to total energy, that is EVJ, right. So, now we can determine the number of ways of distribution for this particular ensemble by this formula. So, W is going to be A factorial by product over the volumes, product over the energy levels of the AVJ factorial. As I have been doing, I can now write the capital A also as sum over V, sum over J of AVJ factorial and divided by product over V, product over J, AVJ factorial. And now we will have certain constraints. The first constraint is the same as what we have been doing, that is, if I sum over the occupation numbers, we should get the total number of systems in the ensemble, that is capital A, that is summation over V, summation over J, AVJ is equal to A. Same applies for the energy. So, if I sum over the energy of all the systems in the ensemble, that is going to be a sum over AVJ and EVJ, that is the energy of AVJ systems, that is equal to some constant E. And finally, we can also sum over the volumes in this case. So, if I sum over volume of all the system, that is equal to some large V. Keep in mind that whenever we define these constraints, we assume that for the total system, if I sum over all the volumes, if I sum over all the energies, that should be a constant variable. That is on the assumption that there is an infinite bath and the systems together with the bath become like an isolated system, because I am considering both the system and its surrounding. Systems interact with the bath, that is how we get constant temperature and pressure, but systems do not interact between themselves, so as to speak. So, therefore, I can define three constraints. Let me call it G1, G2, and G3. Now, these constraints will appear as a Lagrange multiplier in the maximization problem. So, let us define the multipliers as alpha, beta and some theta. This beta is equal to 1 by kBT as earlier, because the energy constraint is going to be the same as the canonical ensemble that we have done earlier. So, the beta, the multiplier, is also going to be the same. However, this theta is a new multiplier that come here. Alpha existed as lambda 1 in the previous problem, but in any case this will come from the first constraint later in the derivation. So, anyway the alpha will not appear in the final formula, but beta and theta will appear. So, therefore, the maximization problem is dou ln W by dou AVJ minus alpha multiplied with dou G1 by dou AVJ minus beta multiplied with dou G2 by dou AVJ minus theta dou G3 by dou AVJ, and this has to be set equal to 0 for the most probable distribution. So, now the ln W can be written as, using Stirling formula, summation over V, summation over J, A V J ln of summation over V, summation over J, A V J minus summation over V, summation over J, A V J ln A V J. There is one more term in the summation here that is equal to this, and that also appears in the second term, and they will cancel out. So, therefore, if I use the maximization formula, what do I get here is summation of V, summation of J, A V J divided by summation of V, summation of J, A V J, that is when I take a derivative of the ln term, plus ln of summation of V, summation of J, A V J multiplied with 1, because again the derivative will apply to only one term in the summation that corresponds to the particular value of A V J. Similarly, for the second term, we are going to have now the derivative will apply on only one particular term for a particular value of V and J, and therefore, we will have A V J by A V J minus ln A V J, and then we have these three terms. So, the first one is alpha dou G1 by dou A V J. G1 is right here. So, if I take a derivative, that is equal to 1. So, we have alpha appearing here. Then we have dou G2 by dou A V J, that is right here. So, if I take a derivative, we will get E V J appearing there. So, we have beta multiplied with E V J, and finally, the third term will be theta multiplied with this volume. So, if I solve this, what I have is AVJ is summation of V, summation of J, AVJ, which I can as well write as capital A, exponential of minus alpha minus beta EVJ minus theta V. So, therefore, I can define the probability of having the volume V and energy level EVJ as AVJ by capital A, and since we are referring to the most probable distribution, we can put a star here to indicate that that is the occupation number for the most probable distribution, and that is equal to exponential of minus alpha minus beta EVJ minus theta multiplied with the volume. So, therefore, we have got the expression for the probability. So, first thing we do is to find these Lagrange multiplier. So, the first one alpha will come from the normalization, that is summation of V, summation of J, AVJ is equal to A, which I can also write as summation of V, summation of J, PVJ is equal to 1. So, if I do it here, what we have is summation of V, summation of J, exponential of minus alpha minus beta EVJ minus theta V, that is equal to 1. So, therefore, since I can move this exponential of minus alpha outside, it does not depend on volume or J, that is equal to exponential of minus alpha is equal to 1 over summation of V, summation of J, exponential of minus beta EVJ minus theta V. So, if I put this thing right here, what we have is exponential of minus beta EVJ minus theta V by summation of V, summation of J, exponential of the same quantity. So, now as we have been doing, the denominator becomes the partition function. So, in this case, this quantity is the partition function for the isothermal isobaric ensemble, and let me call this some delta, that is the partition function for this ensemble. So, just like what we had for the canonical ensemble, that my Helmholtz free energy was minus kBT ln of the partition function for the canonical ensemble. If I am doing it for the grand canonical ensemble, we already know that the corresponding thermodynamic function is the Gibbs free energy, and that should be equal to minus kBT ln of the delta, that is the partition function for the isothermal isobaric ensemble. Now, we can go ahead and try to find the average properties in this particular case. So, let us say for example, I am interested in the average volume. So, the average volume will be summation of V, summation of J, PVJ multiplied with V, that is I am multiplying the probability to realize the volume with the probability. So, keep in mind that I am summing over all the energy levels and all the volumes, that is the mean value or average value of energy we obtain, that is equal to summation of V, summation of J, V exponential of minus beta EVJ minus theta V divided by summation of V, summation of J, exponential of minus beta EVJ minus theta V. Now, this should come from the derivative of the ln of the partition function. That is what we have seen in the earlier case as well. So, in this case, if I do dou ln delta by dou V, what we will get in this case, if I do dou ln delta by dou theta, because theta is the multiplier in this case. So, if I do this in here, what we have is 1 by delta dou delta by dou theta, that is delta will appear at the denominator, and then I am taking a derivative of this particular sum, that will be summation of v summation of j exponential of minus beta e v j minus theta v multiplied with the derivative of this quantity with respect to theta, that is equal to minus v, and that should be equal to minus v bar, as we have already seen there. So, now if I compare that with the differential form of dg, the Gibbs free energy, what we see is that dg is minus s dt plus v dp plus summation of j mu j dnj. It does not matter if we are doing for a multi-component system, because the derivative does not apply to the last term in this case. So, what we have is dou g by dou p at constant temperature and number of molecules, that is equal to volume. But we have already established that G should be equal to minus kBT ln of delta. So, therefore, from here what we get is dou ln delta by dou p is equal to V divided by kBT. Why is that? Because I am putting G is equal to minus kBT ln delta there. So, minus, so there will be a minus sign right here. So, now if I compare this expression with the earlier expression, what we may notice that the theta must be equal to my pressure by kBT, or in other words it should be equal to beta multiplied with the pressure. So, therefore, if I go back here, I can now replace theta with beta p, and therefore, what we have is my p v j can be set equal to exponential of minus beta multiplied with e v j plus p v divided by summation of v summation of j exponential of minus beta multiplied with e v j plus p v, or in other words the partition function for the isothermal isobaric ensemble is summation of v summation of j exponential of minus b beta e v j plus p v. Now, let us say if I am interested in the fluctuation in the volume in this case. So, now since volume is a variable, we will have an average value and we will have a fluctuation that we can define again as v square minus v bar square, that essentially is same as v minus v bar square average, that is the standard deviation square or the variance, that is equal to summation of v summation of j v square p v j minus summation of v summation of j v p v j, that is my v bar whole squared. So, this thing will be equal to summation of v summation of j exponential of minus beta EVJ plus PV multiplied with V square divided by summation of V summation of J exponential of minus beta EVJ plus PV minus of summation of V summation of J exponential of minus beta EVJ plus PV multiplied with V divided by summation of V summation of J exponential of minus beta EVJ plus PV. So, you will find a lot of similarity in the math. So, if I look at the grand canonical ensemble, we were looking at the fluctuation in the number of molecules. The kind of formula that we had was similar to this, except that we had n in place of V, but the basic schematic, the basic way in which we are doing the math is very similar to what we have been doing. So, this should be equal to the second derivative of the ln delta, that is the partition function in this case. So, let us see if it is indeed true. So, let us say if I start with delta, then dou ln delta by dou p, we already have seen that it is equal to the minus of the volume, but let us say we do it again. So, this thing will be 1 by delta and dou by dou p of summation of V summation of J exponential of minus beta EVJ plus PV. So, that is, let me write what the delta is in this case. And then I am taking a derivative with respect to P. So, you will have summation of V summation of J exponential of minus beta EVJ plus PV multiplied with the derivative of this quantity with respect to the pressure, that is minus beta multiplied with the volume, and therefore, we pretty much get the result as earlier. Keep in mind that earlier we were doing with respect to theta, but theta is equal to beta multiplied with the pressure. Now, let us say if I do the second derivative, so I have to differentiate whatever result we have obtained with respect to the pressure again. So, you will have the denominator multiplied with the derivative of the numerator minus the numerator multiplied with the derivative of the denominator divided by denominator whole square. Essentially, I am using the formula for division. This is equal to V du by dx minus u dv by dx by v square. Let us see what it gives me. So, in the denominator we will have summation of v summation of j exponential of minus beta EVJ plus PV whole squared, and then this entire thing, the denominator will appear here. So, you will have summation of V summation of j exponential of minus beta EVJ plus PV multiplied with the derivative of the numerator, that will be summation of V summation of j exponential of minus beta EVJ plus PV, and now we again take a derivative of this, that will give me a minus beta V again, and you already have 1 minus beta V. So, you will have beta square V square, and in the second term what we have is the numerator appearing as it is, but then the derivative of the denominator will be the same as the numerator. So, you will have a beta v appearing here and the whole square of this quantity. So, now if I notice the first term, you will have cancellation of the numerator here. So, what we have essentially is beta square v square bar, and the second term is essentially beta square multiplied with v bar square, and that is essentially beta square multiplied with v square bar minus v bar square, and therefore, I can write my fluctuation as 1 by beta square dou 2 ln lambda by dou p square. Since we know that theta is equal to beta p, it is naturally dou 2 ln delta by dou theta square. So, using that, what we have been able to establish is that we have a general protocol once we know the partition function, and there is a way the partition function is being defined. The partition function is always defined by summing over the Boltzmann factors, but then there is some correction to the Boltzmann factor depending on the ensemble under consideration. And in fact, all the partition function to that extent is also related, because I could as well have written this delta, for example, by separating the last term. You will have summation of v, summation of j exponential of minus beta e v j multiplied with exponential of minus beta p v, and this naturally is the canonical ensemble partition function. So, first of all, the partition function are the normalizing functions and generating functions. They can be used to generate not only the average value, but also the fluctuations of the quantity. Now, the key thing to remember is that our ability to find the fluctuations will depend on the ensemble under consideration. So, let us say for example, if I talk about volume fluctuations, it means that volume is not a control variable. That is only possible when we are doing the isothermal isobaric ensemble out of all the ensembles that we have considered. In all the other cases we have considered, the volume was a control variable. So, the volume fluctuation is only defined in this particular ensemble. So, this idea of computing this will only make sense when I am looking at the isothermal isobaric ensemble until in all the ensembles that we have done so far. Similarly, if I talk about fluctuations in the number of particles, that will make sense only in the grand canonical ensemble, and therefore, in that case we should use the grand canonical partition function. So, ultimately the basic scheme or the way to think about any thermodynamic problem is first to identify what is the appropriate ensemble for this problem. Let us say for example, I am interested in the behavior where I am performing experiments at a constant temperature and a constant pressure. What this means is that we have an ability to control temperature and pressure. That is a confusion people always have, that when I say constant temperature and pressure, it does not mean that temperature and pressure are being held fixed for that experiment forever. It only means that I can do it at different temperatures. I can do it at 20, I can do it at 30. We have a mechanism to control temperature and to run experiment at a constant temperature. Similarly, the same applies for the pressure thing. So, if I am saying that I am doing at a constant pressure, it means that we can do at any pressure value in any experiment we have ability to control the pressure variable. So, if for example, we are doing at constant temperature and pressure or controlled temperature and pressure, then in that case I will seek to find the isothermal isobaric ensemble partition function, that is the delta in this case. If for example, we are not doing experiments at constant temperature and pressure, let us say we are doing at constant temperature and constant volume. In that case, we will go for the canonical ensemble partition function, and in that case the Helmholtz free energy would make sense, unlike the Gibbs free energy in the previous case when I was doing constant temperature and pressure. Similarly, if for example, I am working with constant number, constant volume and constant energy, in that case entropy becomes a thermodynamic function, and we are talking about the microcanonical ensemble partition function. So, therefore, the key idea that I want to re-emphasize is that for any thermodynamic problem, the first objective is to find what are the control variables in this problem, and once we have done that, the next part is to find what is the partition function. We have not so far discussed how to get the partition function, because even if I have said the delta is this, I do not know what these EVJ values are. These energy values will depend on the discrete energy states. So, in principle it comes from quantum mechanics. We have not said how it comes there. We have not even said how will I find the pressure and volume. All of this can be found once I know the partition function, but we do not know the partition function itself. We know what properties it should satisfy. If I know partition function, I can generate the average properties, I can generate the fluctuations, but all I have is an expression of the partition function in terms of the energies that is still unknown to me, and therefore, we need to find a way to find that particular partition function. So, in the next lecture, I will say how that partition function is derived from the what is known as the molecular partition function. We take an ideal gas example, and so how can we derive the partition function for this case. But going further, I will also discuss what is not known as a lattice model, that is a simplified way of estimating the partition function, right. It turns out that for all complex scenarios, the partition function is highly non-trivial, because you can just imagine if I have millions of molecules or billions of molecules, in reality we are talking about systems having moles of molecule, that is 10 to the power 23 or higher molecules. So, in that case we can imagine there will be like a large number of possible states. So, whenever I put this simple looking sum over all the volume and all the j, that sum will contain a very large number of terms that corresponds to the number of possible conformations. So, even though once I know this partition function and I can find everything, getting the partition function itself is a challenging affair. It turns out that we can have some ways to estimate the partition function or some ways to approximate the partition function, that is one way of doing it, and the other way of doing it is to use the molecular simulations, where we will see how we smartly handle our ability to not compute the partition function and we can still get the average properties. So, with that I conclude this lecture. Thank you.